So our main objective is to improve the continental scale hydrological simulations at a higher spatial and temporal resolutions. So which is important to represent the topographically driven groundwater and streamflow generations in the many hydrological and geothermal applications. And it's also important for the geological heterogeneity across different scales from 100 of meters to thousands of square kilometers. So our main focus is to improve the spatial resolutions of these large-scale hydrological simulations, and also to improve the geological information in our models, and to do the uncertainty quantification too. Yeah, so the main task that includes in this scientific challenge are to perform the exascale hyper-resolution hydrological simulations, and also to connect those simulations with the hydropower modeling in the Italian Alpine regions, and to also do some hydrodynamic simulations for the flood forecasting. So the other two tasks are also related to the geothermal modeling. So we have there are 4 partners, so ULIC and the University of Trento, Surfex, and the University in Aachen. So this is just an overview of the first task, which is related to the performing these large-scale hydrological simulations, and the objective is to improve these continental scale hydrological simulations by using a higher spatial and temporal resolutions. So this task have 3 subtasks where we wanted to set up the model for the over Europe, and then we also wanted to do the model evaluation and validation with observational data or measurements, and to do the uncertainty quantification by using the data assimilation approach. So this is just showing our model setup. So we are using this power flow model, which simulates all the subsurface hydrological processes, and which is also coupled with the land surface model, CLM. And this CLM power flow is also coupled with the parallel data assimilation framework, which we use to merge the observational data to our model estimates in order to improve our outputs. So this we have been set up this model over Europe at a 3-kilometer resolution currently, and so the problem size for our model is around 1500 times 1500 times 15. So it's a very computationally expensive, and we run this at hourly time scale. So on Joule's machine at the JSC, so it took about 4 to 7 hours for 1 week of time period of simulations if we use the 192 processors. And also 1 year of simulations, we need like a 6 terabyte of data for the storage. So yes, these are just also showing the inputs that we needs to run these model simulations, like the elevation data, the land cover informations, and also the soil properties information. So that's and also other meteorological forcing that goes into these models. Yeah, so using this model, we now finished the model simulations for 16 years of time period, but for this work, we have only used the standalone CLM models, but coupled with the data assimilation framework, so that we can improve the soil moisture estimates in our from our model outputs. So yeah, so we have developed this soil moisture, we call it the surface soil moisture reanalysis data, and yeah, so it's this is the data sets which includes consists of the daily soil moisture at a 3 kilometer resolutions for 16-year over Europe, and it's also freely available to download from these websites, which can be used in many hydrologicals and agriculture applications. Yeah, so we are also conducting some model validations by comparing our model outputs with the observational data sets, like discharge data that's are measured for different rivers in Europe. So this figure is showing an index of the model performance for the discharge simulations from our CLM model, and so these points are the measurements or the gauge stations at the different rivers for 800 rivers in Europe, and this index means that if so it's from 0 to 1. So 1 means that we have a best match with our model outputs. The observations match have a good agreement with our model outputs, and the 0 means that we have bad agreements with our model results. So anywhere where you see blue, which means we have a good agreements, and so this and this is also some time series for just an example. Yeah, time series of the Streamflow simulations for the 16 years of time period for 3 rivers in Europe, and which is so just looking at the comparison, how the observation, how our simulated discharge compares to the observations. So using this simulated discharge, then we can use this simulated discharge to the hydropower modeling framework, and which is the next step. And so this is the work that University of Trent, the group at the University of Trent is working on. So we have like 4 subtasks to implement the hydropower models in the Alpine region. Yeah, so the first task includes to develop this routing models, which can route the stream flow from the grid cells locations to different locations where we have the reservoirs are located. So they are also working on to improve their routing model so that it can be computationally efficient and can be applied to large-scale simulations. Yeah, so and then this this routing model also include the explicit simulations of the artificial infrastructure, such as the human systems like reservoirs, reservoirs channels, and plant. So this model can then explicitly model those reservoirs at a different locations on the rivers. So this is just a diagram of the schematic diagram of the reservoir modules, which shows different stages of the water level in a reservoir. And then, yes, so they have started with at a small scale for one small catchment, and using this model, they have applied this model for this catchment in Eastern Alps, and it's which has 30 hydropower reservoirs and also 22 storage hydropower plants. So in this time series, they're showing how their simulated hydropower predictions compare with the observations for one of the hydropower reservoir. And then this, so they start at a small scale, and then they wanted to extend these simulations over the entire Italian Alpine region. So, so they have done some preliminary calibration of the model, and to compare the stream flows at these different locations, and then in the next step they will do the simulations of the hydropower productions in this region. Yes, the next two tasks are about the geothermal modeling. So they are working on predicting the optimal borehole locations and logging depth for parameter estimations for geothermal reservoir using an optimal experiment design, OED. So they have 7 tasks, and currently they are working on this OED simulations and developing a post-processing workflow. Yeah, so this is just an example of the approach that they are using. So this OED approach, which has been already used in different publications, which is feasible for finding borehole locations in 2- and 3-dimensional reservoir model, which also minimize the uncertainty of estimating the hydraulic permeability. So like in this diagram, you can see which is the 3D geothermal reservoir models, and it's showing the direction and magnitudes of the subsurface flow, and also these dark blue spots are the optimal locations of the boreholes. So they wanted to extend this approach to also predict the optimal logging depths or the logging interval which is needed for the temperature measurements. Which would be using to estimate not only the hydraulic permeability but also the thermal conductivity. So they're currently working on to do some sensitivity analysis of this OED approach, comparing with other data sets and previous simulations. Yes, they are so also working on developing like post-processing workflow of this SheMet suites and using the EoCoE output framework with the Jupyter notebooks, so that they can do a lot of other synthetic tests to efficiently use this approach. So for this, they are now developing this test model suite for the OED studies where they wanted to do the synthetic test with known parameter for sensitivity studies. Yeah, so this diagram is just showing the examples of using this post-processing workflow. Yeah, this is also an example of their 2D test model. The geothermal, which is the cross sections of the geothermal reservoir above salt diaper, and then this. So this is like a cross sectional by two. Yeah, showing the two high permeability faults pathway for adductive heat transport. So. So these are the example, some of the examples that that they can check their results with the post-processing workflow that they are working to develop. So yeah, so their future outlook is to predict these optimal locations for this temperature measurements. For estimating permeability and thermal conductivity with the least uncertainty. So this is, yeah, so this is what I have for now. Thanks.